some CCP4 processing. And during this workshop, we have learned a lot about getting 2D crystals and recording data, both in image and diffraction mode, and processing this data until the stage that we have fitted and sampled lattice lines. There hasn't been so much said about calculating maps. That's sort of a very simple step in a way. Richard Haidt yesterday talked about refinement, model building, and in the student presentations yesterday we had some discussion about comparing structures and calculating difference maps. So there is sort of a borderline here, which takes us from the very specific, very specialized EM world into the X-ray world. And as Richard Haidt mentioned yesterday, this brings us into a world where we have a lot of programs already developed, and there is a lot of information available on mail service, for instance. So I thought I should explore a little bit more in detail the latest steps here. And I have made up a scheme which is a little bit more complicated, but contains basically these steps here. And so if you cannot see this in the back, I will blow up the different steps here later on, so don't worry too much if you don't see all the details here. And this scheme, I have the convention that the normal text is what you have. So structure factors, for instance, and capital letters is what you want. Maybe you want to have a simple map, you want to do refinement, and in italics are the program steps that brings you along this scheme. I've also included some comments for the different steps, and on purpose I have split it up a lot of the pre-processing steps here, which can be fused into more or less one step, but I've subdivided these into individual steps and to be able to make some comments about the different steps also. So the first thing here is that after the electron crystallography processing, we are left with HK Z-star information along the lattice lines. I should also say that this scheme is a little bit, it's maybe not, doesn't represent an actual case. I've included here intensities and phase information. Normally, if you only have images, you have amplitudes and phase information, or if you have diffraction, you have only intensities. But I've sort of mixed this together to make it more complete. So the next step then is to transform this Z-star to an L index. And this is a simple operation, and we do this by a simple Python script. But at this stage, it may be, one can start to consider later steps. We are going to calculate a map eventually, and a map in 3D has 3 directions, X, Y, Z. And these can be defined. This is taken directly from information from the map calculating program in CCP4. So there is a fast and a medium and a slow axis for this map in the XYZ direction. And in electron crystallography, we always have flat crystals, and we always index HK along the plane of the crystal, and L is in the normal direction. But in X-ray crystallography, crystals grow in 3 dimensions, so there are different conventions here. And this is dependent on the space group. So in general, the fast, medium, and slow axis is in the order y, x, z. And this is true for all space groups with space groups number greater than 18, three-dimensional space groups number greater than 18. While for lower symmetries, all monoclinic and three orthorhombic, the required axis order is Z by XY, which gives Y sections instead. And this can be taken into account already at this step when we transfer the HK Z star values to HKL by simply making a permutation of the axis. It can be taken into account later also, but there's always a risk of making some mistakes there. Next step is to transfer the text file into a binary file, and this is the binary file in the MTZ format. And a program which does this in the CCB4 package is F2MTC, and it can take any text file. It's a whole type Fortran format statement which defines the text file. So this MTZ format now has a number of columns, and these columns are labeled, and there are a large number of labels that can be put into an MTZ file, and many of these are specific for X-ray crystallography, so you don't have to bother about them. I highlighted ones that are most important for our usage. So intensities, amplitude values, sigmas, figure of merit, phase information, and so on. So the next step here is to transfer, if we have intensities, to transfer these to amplitudes, and this can be made by the truncate program in the CCP4 package. This also gives a Wilson plot and an overall B factor for our data. Next, we have to uniqueify the data to generate a unique list of reflections. Richard talked about that yesterday, and also include a free R flag column. So this puts, if you set aside, let's say, 5% of your data for the R free calculation, the data is put into 20 bins defined by the free R columns. So there are, each reflection is assigned one of these bins, and then you can choose which one you want to use for the R free calculation, once you want to set aside for the R free calculation. Then there is a program SF Tools, which I mentioned here because it's quite useful for manipulating MTZ files. So you can, for instance, remove the intensities if you have converted from intensities to amplitudes. You can do this in one step, but just to illustrate the things that can be done with SF Tools. In some cases, it may also be informative or useful to expand from your symmetry to P1. So this is not, we discussed that yesterday, this is not, of course, not calculating the structure in P1. This is expanding a symmetrized data set into P1 in order to be able to calculate a whole unit cell with symmetry. So then we have reached the stage where all the pre-processing has been done, and we are now approaching the level where we want to do something. We want to maybe calculate a simple map. And so this is highlighted, the second part of the flow scheme here. So the simple map is calculated by the FFT routine in CCP4 package. There is a special routine if you have a P1. So if you have expanded your data set to P1, for instance, you can use a special FFT program which is called FFT Big. So to calculate a simple map, it may look very simple, and in principle it is very simple, but you may encounter some unexpected maps maybe, and I'm just mentioning this so if you do this for the first time, you should not be surprised if your first impression is that something is wrong here. So let's say we want to calculate a map which covers this model which we have here. Okay, we go on and use the FFT program to calculate the map, and this is what comes out. And you're maybe at first sight not so happy with it. So there are some, not errors here, but there are some things which make you a bit confused. So there are two things here. One is obvious, the origin must be shifted somehow here. And the other thing is maybe not so obvious when you look at it in this way, but if you compare to this map, you see a large difference. And the difference is that here you have used only the data in the asymmetric unit. So this crystal here has a P6 symmetry. So your map will only be one asymmetric unit. And maybe this asymmetric unit does not cover your protein molecule that you want to cover. So you can manipulate with your maps and expand it to cover the whole unit cell. And the next thing here is to shift the origin so that the map really covers the model which you're interested in. So this is all done can be done with CCP4 routines which manipulate with the maps. You can extend maps, you can shift maps, and so on and so forth. So this is calculating a simple map. To the left here, I've included a step for combining structures. And the principle in CCP4 is to not to have two separate files defining the two structures, but to merge them together. So this is done by the program CAD, which takes data from one structure and adds in information from another one. So as you can see here, the MTZ file now contains not only the HKL, the amplitudes and phases from the map up here, but also from this other map which comes from somewhere. And then having that, you can, using the FFT routine, calculate difference maps. And often it's useful to calculate the differences in both directions, because some visualization programs, at least maybe I've seen some versions of Chimera which doesn't handle negative density, so it might be a good idea to calculate the differences in both directions. This is very simple. So. The other branch here is related to the refinement step, and for the refinement, you first of all, in CCP4, the traditional refinement program is RefMac5. Of course, you can use other refinement programs as well. You need to put in a model, or maybe do model building from your map as an input here. then calculate difference maps. And as in X-ray crystallography, we are calculating difference maps with a weight so that the observed structure factors are twice the calculated structure factors. This is two FO minus FC maps. But you also calculate the FO minus FC maps to identify differences between your model and the map. And this might require rebuilding then in COOT or any of the other model building programs. And then validation, there are several programs in the CCP4 packages for validation of your data. And if you're not satisfied here, you go back to a refinement. So this is a cycle which may go on for quite some time. But when you're happy, then you stop the process. So I thought I should include also another scheme here, which is one application, maybe a little bit more general application that can be used also for in single particle cryo-EM. So I was interested in validating single particle cryo-EM maps, and we heard a lot about this from Richard Anderson on Wednesday evening in a very general perspective when you have no prior information about your structures. But in this case, I wanted to take advantage of the fact that in many cases, in many single particle cryo-EM projects, I think there are X-ray structures or maybe other cryo-EM maps which you can compare with. And if you have a reliable X-ray structure, you have a very reliable structure to compare with. So I was curious if this could be done using existing programs in the CCP4 package. So here, this is a map. It could be also, of course, a low-resolution electron crystallography map. And this is a CCP4 program which calculates structure factors from a map. And you can use the same program also to calculate structure factors from a model. So if you pick out a model from the PDB, you can calculate the structure factors if they are not deposited in the PDB. Of course, you can calculate a simple map from this structure at any resolution that you're interested in. But then you can also use this program CAD to combine these two files together. And so you have this combined, merged MTC file here. And then there is a program in the CCP4 package which makes comparisons in real space. So I was interested in the scaling, but also in the resolution-dependent scaling. In other words, if refining a B factor. So this program can be applied now, and I want to give you, and if this program refines scale and B factor, and it does, and it also gives an R value for the comparison, you can use that to scale your amplitudes here and to calculate as accurate as possible, I think, difference maps. And I will give you one little example of this process. So this is an output. The RStats program gives a lot of information for the refinement, but this is a summary here. So these are ribosome structures, and these are 4 structures from our lab, which this specimen suffers from a heterogeneity, and we have split it up the complete data set using Shor-Scherer's maximum likelihood approach. So the particles included in each of the data set is not that great, and the resolutions are not that great either. But using this RSTATS program and comparing now to a ribosome structure, 3.5 angstrom ribosome model from E. coli, one gets R values here, a scale factor and a refined temperature factor. And our impression from the beginning was that this particular structure here was the most accurate one, and indeed it gives the lowest, by far the lowest R value here also. It gives a reasonable temperature factor, given this low resolution. So this seems to make sense, and I also put in here two structures which have been deposited in the data bank. And these are two ribosome structures from the Frank group, and these are at slightly higher resolution. So this is Fourier shell correlation 0.5, so maybe they are a little bit better also, as suggested by Richard Henderson on Wednesday. These give R values in the same range, scale factors which are closer to 1. And it was interesting because I couldn't pick out from the papers if they had applied a B factor to their final maps, if they had boosted up the low resolution information. But I think it's quite clear from this analysis that they must have done that, because you get here a temperature factor which is very close to 0. And indeed, for this particular structure, you get a plus value. So maybe they have boosted it up a little bit too far. Well, there are no error figures here on the temperature factor, so maybe it could be also close to 0. But so I think this could be quite useful, and one could put in any deposited map here compared to X-ray structures. I should mention also that, of course, these structures contain. I said I'm comparing to an existing naked ribosome structure. So these structures contain some additional densities, some factors which have been added in. So they are, of course, not identical, but with the great mass of the ribosome and these additional factors not being too large, then the comparisons in this case may be relevant. And given this refined scale factors and temperature factors, one can calculate difference maps. And I give one example here of the kind of information that could be obtained in this case. So comparing one of our maps to the E. coli structure, it gives a difference map here, which is very clear. And this is at the interface between the two ribosomal subunits. There is a more accurate map from Thermophilus, a 2.8 angstrom map, also, which contains, so the E. coli map doesn't contain this L31 protein, or rather it's positioned at the wrong place in the ribosome, it turns out, because the Thermophilus structure has mapped the L31 protein in this region here. And it's a very, to me, it looks more or less like a random coil protein, but nevertheless, in the cryo-EM structure, it comes out as a very nice difference density. And indeed, analyzing the difference between those two ribosome structures, where the E. coli map lacks parts in the models as compared to Thermophilus structure, indeed, all the differences that we could observe could be explained in this way here. So this was my last slide for this short presentation. And the plan is to have a little session in this afternoon. So we tried to set this up yesterday, and hopefully it's going to work. And so for those of you who are interested, it may give you an opportunity to explore a little bit of what I've been talking about here. Okay, thanks.
Do you have a zoom out image for this? I want to know where is the exact nucleus in the reaction.
Oh, I don't have it here. No, sorry. This was not my intention actually to include this. I didn't bring it along. Yes, as you see, it's at the interface between the subunits, and if you're familiar with the ribosome structure, this is the so-called A-site finger. This is another thing here. The A-site finger is lacking in both the E. coli and the Thermophilus structure. This one here. I don't remember. Andreas? This is the MRC convention, so we use the figure of merit, and this is, yeah.
Now, the other question is, at the given point, we do the sampling along the star to get the L. And each of those, of course, is the correlative measurement of many, many points along the lattice line. And each point there has a certain sigma, but the value we actually stick in with the CCP4 wasn't the sigma then, because it's the result of many measurements. Just take the one which happens to be where you sample.
So I'm not quite sure, but I suppose it has to do with the observations and the lattice line fitting. So the deviations of the experimental measurements from the fitted lattice line. This exactly how this is calculated. This must be in the latline program, but I'm not sure exactly how this is done.
Sigma. Well, the sigma on the amplitude comes down to that line. How it calculates so you don't use it in the next one.
Indeed.
The only error that you're using is the figure of merit, which is the cosine of the phase error. Yes.
Yes.
Okay. That's all you use. Yes, you mentioned that. But the other thing is, we compare to, I mean, if you want to do refinement and stuff like that, you need also the sigma of the intensity or the sigma of the amplitude. Is that
Many of the CCP programs require that you have a sigma of your observations.
Yes. Now, if you measure in X-ray, of course, you have your 10 to the 8th or so unit cells that contribute to your intensity measurement. So even though you only make a measurement at a point, this will be a very high quality measurement. So what I want to say is the sigma in X-ray is not more than the sigma that you plug in. And I have no idea whether that makes any difference or not. And if that would, in a way we give away all the many measurements we did along the continuous lattice line. And somehow it is not clear to me how one can actually take advantage of this multitude of information.
I think the only way around this is to collect more data so that you bring down the sigmas. I think in Richard Hyde's presentation yesterday, we saw some lattice line fitting where the sigmas were really huge, yes. And this information will be lost in the processing later on. So you have to bring that down, and the only way out, I think, is to collect more data. Okay.